Okay, I want to talk about two things today. And if you remember when we described the class, the first part is about learning content, right? And this might be the driest of all classes, because what I'm going to do is essentially teach you a dictionary. So you don't need me to teach you a dictionary, but I am here. I'll try to make it as light as I can for you. At the beginning, seems like you'll be reading a dictionary, and it's dry, and maybe difficult. But this is a language we're going to be using for the whole rest of the class, and for the whole rest of your professional life if you come across welding. So, two things. I'll teach you some words, and then I want to get into something particular of welding, that is welding symbols. And they're super cool because it's almost like writing in Egyptian and making sense out of it. So it's good to be initiated in that. Let's discuss about terminology then. So, all right. Some basic welding terms. I'm going to say these words. Let's see. I'm going to say these words. I'll try to explain them to you. You must know them at some point by the time of the exam. Oh, by the way, one of the exams we had scheduled for Thanksgiving is not going to be on Thanksgiving. It's going to be on the following Tuesday. We're going to send a notice so everybody's on the same page. So, all this, if it doesn't make sense immediately to you, will soon. One term, travel speed. So when you're welding, if you remember I mentioned you melt some things and you don't melt some things. Okay, that is because you're moving. You can move fast and melt little, or you can move slow and melt lots, right? That velocity at which you move is called the travel speed. Also, some welding processes, you have a wire. You start to unspool the wire, you melt the wire, right? And you'll know everything about it, and you're going to see them in action. So the wire comes at a velocity too, right? That is what is called the wire feed speed, right? Then in electric welding, you have two big cables because the voltages are relatively low, but the currents are high, right? And those big cables are called the leads, right? Also, in arc welding, and we'll have a whole section on arc, right? But I'm just trying to introduce these terms. The arc, that if you remember, we talked about how the electricity was jumping from the electrode to the plate across a gap, right? And it's because the gas there is very hot because it's ionized, right? And this gap is called the arc length, right? More things that relate to electric welding. If you remember too, I mentioned there's so many types of joining, from bolts to glues to brazing to arc welding to electric welding to solid state welding. So many of these terms are specific to arc welding. That is a small subset of welding, but is the subset in welding in which we do almost everything here in the province and much of the world. So because there's electricity in electric arc welding, you have DC when it's direct current, or you have AC when the polarity, the current goes in both directions. This is also called variable polarity. When you have DC, you're going to see, right now it might not mean much to you, but the electrode might be positive or the electrode might be negative, and it means a whole lot. The welding arc acts as a rectifier, so it's not the same pushing the current in one way than pushing the current in the other way. This I put here so you know, but for some reason that is historical, in welding people typically call electrode negative straight polarity. And when the electrode is positive, they call it reverse polarity. That's historical reasons. Because some processes run always in electrode positive, and nobody would say that the process is reverted. The constant, when you run a process, and I understand you guys probably have precious little electrical engineering background, but some things you would know. For example, you put a current, and if you have a load, it's going to give you a voltage. Or you put a voltage, and if you have a load, it's going to determine the current. So welding is a load, And the machines you have can run either by giving a voltage and whatever be the current, right? And that is called constant voltage, CV. Or sometimes it puts a current regardless the voltage, right? That is called CC. All this matters because some processes are always run, well, are typically running CV. Other processes are typically run in CV or CC, right? And there are good reasons for that. And we are going to explore those reasons as you go through the class. Also, all this is relatively old school. But now the welding machines are controlled by computers. And when you come to the lab on Thursday, you're going to see that in reality, a welding machine is now a computer that gives you electricity. And now it can give you anything you want, not just constant voltage or not just constant current. It can give you all kind of variable electricity that is specially tailored to give you the best possible weld. This is quite common. 3 more common words. Preheat. So let's imagine we melt steel. We're welding steel. Steel will always melt at the same temperature. Now, if the steel is at room temperature, the jump to melting is a given jump, and the heat transfer associated with that delta temperature is whatever. But if you're welding at -40, the jump is even bigger. If you're welding at 200 degrees C, the jump is smaller. I have a question for you. I haven't taught you anything, but intuitively, if I have a higher preheat, right? I'm welding on something in which I increase the preheat. Do you think the weld is going to cool faster or slower? Slower, right? So I didn't teach you, but you know something that is super important. So how many of you are Mari here? Okay, so if I cool down slower, and I'm working on steel, what do you expect the steel will be, harder or softer? Softer, right? So you already know something extremely important about welding. If you have a weld that is too hard, right, then you can increase the preheat, and the weld is going to be softer. And this has nothing to do with the heat of the preheat softening the metal, right? This is amazing. And of course, everybody knows this. But not everybody knows why. Actually, many people don't know why. And people would start saying, oh, I'm a good welder. I don't need no preheat, right? And they say, no, you don't understand. Like, it's about the laws of nature. It's not about your hand, right? So we're doing awesome. The other thing is called interpass temperature. So imagine you are welding something that has many passes, right? You do a pass, it's going to be hot, right? If you ever saw a weld, you don't touch it right after you pass. If you do another pass, it's going to be pretty hot to start, and it's even going to be hotter when you finish, right? So it accumulates heat. This is a problem typical of additive manufacturing, right? But in welding, which we don't call additive manufacturing, still, you might be adding metal, and can get hotter and hotter and hotter. Now, if you have a stainless steel, any of you know if welding when it's too hot can be a problem? Oh. Timaris?
Corrosion caused by the chromium melted in the microstructure.
It didn't melt, but what you said is right. You know the name for that? It's called sensitization, right? So if you have a stainless steel and it gets too hot, you have some little chromium, some little carbon there. You have a lot of chromium in stainless steel, more than 13%. And if you heat it up, the kinetics will be that they combine and make chromium carbide. Now, chromium carbide is super good in many things, but in stainless steels, it's super bad because the carbon now absorbs the chromium and it's not stainless anymore. And in addition, you have a precipitate that makes the toughness being horrible, right? So if I'm welding stainless steels, do you think I care about the interpass temperature, or I just would let it like increase temperature forever? No, right? So, for example, in stainless steels, interpass temperature is very important. And the consequence of interpass temperature is not just words. It means a welder made a pass, and the welder has to step back and wait. But you're paying the welder a welder wage, while the welder is just waiting. Of course, like companies hate this. On the other hand, the risk is sensitizing the steel, right? And there is big fights about this between people who says, I want quality at all costs, and people say, I want cost which I can survive. And that comes down to, okay, what is your interpass temperature? So you are in the third lecture of this class, and you're already learning many things that matter very much. And what I would hope is that you don't just read an interpass temperature and take it as God-given, but you understand why it's there, and if it is a problem, you would know what to look for. Is there a sensitization, right? Am I too slow? The last one, PWHT, post-weld heat treatment. So imagine you use the formulas we will teach you, and you end up that you have to, you have a hardness problems, and you come to the conclusion you need a preheat, which you will know how to calculate. A preheat of 650 degrees C, right? Okay, 650 degrees C, the things start to glow red, right? If you're going to do that preheat, it's going to be very difficult. You cannot touch it. You have to handle it with lots of care. It's going to cool down very quickly because it's so hot, right? It's going to be very expensive. That's the bottom line. You might decide you don't want to do that. Maybe you can do it, but maybe, and very likely, you will not want to do it. You don't want preheats that are so high, typically. Okay, so you weld and you have a hardness problem. What do? A heat treatment. You go back to austenite and you normalize, and now you have the microstructure you really wanted to have. But now you have a trade-off. You save the money of a very high preheat, but you have to spend the money on a post-weld heat treatment. Some alloys will give you, for example, in the talk of last Thursday, Dr. Leiner talked about grade 91. Grade 91 is going to give you all martensite if you cool any slower than an hour. And let me tell you, welding cools faster than an hour. So for those steels, you must do a post-weld heat treatment no matter what, right? So this is just a term. We're going to go deeper into all of these things later, but I just want to plant these concepts in your mind. Things that are words, cast and helix. Much of the challenges of welding are reality. When you have a welding that has a wire feed process, the wire comes in a spool, right? You can imagine it's not the same, a wire that comes out of the spool more or less straight than a wire that comes off the spool all crooked. When you see the welding machines, you're going to see that the wire has some kind of amount of free wire extension that is called the electrode extension. If the wire is crooked, that you're going to have a wandering arc because the tip of the wire is moving all over the place. If it is straight, it's better, right? Welding companies, the suppliers, go to great lengths to give you a wire that when you unspool it, goes straight. Actually, they twist it as they spool it such that it would be counterbalanced. If you were to take one loop of wire and you put it on the floor, it's going to make kind of a circle. That's called a cast, the diameter of that circle. And if you look at it from the side, it's not going to be flat. It's going to end up a little bit with a difference of height. That is called a helix. And of course, people say, well, your cast should be very big, right? Because straight wire would be an infinite diameter. And your helix should be very small because straight wire would not be making a spiral, right? Things to think. Many welding problems come back to this. You might be having a brand name wire, and then you decide to buy a super cheap wire. Everything looks the same according to the standards, but then all of a sudden you might have problems that you're missing your joint, and you can come back to this. Okay, or wearing out the contact tip, whatever it is, you're going to see we have sliding electrical contacts, and those can wear out depending on how bent the wire is. More things. And I'm just reciting a dictionary here, so you'll have to put up with me. But please know, if you go to all the exams, the first exam I'll be asking you to regurgitate these words. And second and third exams, I'll just say the words and because it's our common language, and you'll need to do calculations and elaboration over these. Stringer bead means you weld straight, right? As if it was a string. Welders hate it because there is no room for fixing. What welders love, right, is weaving. And you see this kind of stitching process that is not, this is just indicating the path of the torch. And they have many ways of weaving it. They can go in zigzag, they can go back, they Texas lace. I don't know because I don't know, I'm not a welder, but if you talk to the actual welders, oh, they will talk with so many words and so many things about this weaving. The good thing of the weaving is you can fix a mistake because you always come back. But in a stringer bead, no chance. Now, a question to you. In which weld do you think we're putting more heat, in a stringer bead or in a weaving bead? Of course, right? Because I'm moving relatively slow. Now, if I'm putting more heat, do you think it's going to cool faster or slower? If I have more heat, it's going to cool slower, right? Because I need more time to dissipate all the heat I put, right? So, for example, in some stainless steels, you require stringer beads. In carbon steel, very often you would do this type of thing, right? You start to see, and we're going to have formulas out of all this, how things start to come together, how decisions that the welder does out of convenience have an implication for metallurgy, right? Which steel is likely to end up, which weld is likely to end up harder, this weld or this weld, right? This is likely to be harder because has less heat, it's going to cool down faster, right? Which one is more likely to be sensitized? This one, if you have stainless steels, right? Super interesting. In welding, you're going to see how many concepts you either learn about or heard about. They come together and have a direct implication. Another thing is called a stitch weld. This one. The reason for stitch welds is that very often, for example, this member is not load bearing, or the load calculated is relatively small. Now, your weld, you cannot put a nano weld. There is no such thing, and we're going to see why. It's an issue of capillarity. You cannot have a weld that is too small, and you cannot have a weld that is too big. The size is more or less the same. But if you do a calculation that tells you your weld should be 1 millimeter, no, you're going to make welds that are at least 3 millimeters. Now, that would be over welding, that would be overheating things, putting too many residual stresses. So in those cases, you would do a stitch weld, right? And that way, you reduce the residual stresses, right? And you reduce the amount of metal you put, the distortions, you reduce your cost, and you accelerate your time. So all these things, right? Just a word. We're going to be seeing this again and again and again. Other thing, this might be a new word for you. This is a photo of welding. This is the electrode, this is the plate, and this is molten metal here, okay? The molten metal, people call it in a number of ways: weld pool, weld puddle, weld bead. I typically call it a weld pool, right? But what matters is what is molten, the moment it's molten, is extremely important, right? Many things happen there. Chemical reactions, penetration is determined there, porosity, inclusion, all happen inside here, right? Let's just know it exists. We're going to have a whole session on that. Something called keyhole, right? When you're welding with lasers, right, the laser is so powerful, or the electron beam is so powerful, that you kind of drill into the metal, right? And that gives you lots of penetration, and is very desirable in some cases. Sometimes when the welders are using high current, they kind of make kind of a hole in the weld too. And the welder is called a keyhole. But that has nothing to do with the keyhole of a laser. We're going to have a session on the weld pool, and we're going to know those differences. But these are words that the welders use. Tacks, another word. So you're going to weld a pipe, like here. You put the pipe more or less in place, right? But if you're going to weld it, you need to take the clamps out at some point. So what you do is you put some tiny welds here, so the two parts are together. And then when you weld, there are a number of things you can do. This part, welding this part, is relatively easy. Sometimes you just run over your tacks and you remelt them, and it's okay. Sometimes it's not okay, and you need to, after you do a part of welding, you come and grind it out, right? And you keep going, right? So all things that in the end come to affect our science, that the welders talk and do without thinking twice. Another thing, spatter. You see all these little balls of metal there? You're going to spend, if everything goes right, 2.5 hours welding, right? It's going to be, I believe, next week, or the week after, right? You're going to see spatter firsthand, right? The spatter is not good. If you need something that is going to be seen, this is considered a low quality weld. Even if the strength is good, nobody wants a weld full of spatter. Spatter means also steel that you paid for but didn't end up in the weld. It's inefficiency. Spatter also means little bolts of like red hot iron that will get through the back of your neck and give you a pretty good burn. So it's not really safe. So spatter. Some people call it splatter, but I think that typically indicates you didn't finish elementary school. So more terms, backing plate. Sometimes if you're making one big weld, the weight of the metal is just going to fall out, right? The laws of physics, and you would know, say that capillary action, surface tension, can hold a weld only for so long before gravity wins. So when you need to weld a big pressure vessel or a big plate, you would put something called a backing strip. And the only purpose of the backing strip is preventing things falling out. And there are many ways. Some might be permanent, some might be removable, some might be recyclable, right? There are all kinds of backing plates. And what matters here is just to know, if the weld is too big, you might need a backing plate. If you need a backing plate, you need to think. If this was inside a pipe, this is likely to corrode like crazy, right? So you need to take action and either remove it or seal it or do those things. More words. Flux. You're going to hold in your hands electrodes. Here you have a photo of the electrodes. Right? They have this steel rod covered with something. The something is called a flux. Right? And fluxes are just powders from minerals. They don't look like much. They look dirty. They look like nothing. However, they're extremely highly engineered. When we discuss the arc and all issues related to plasmas, you're going to see that these fluxes have a chemical composition that gives you special properties. We are going to have a little section on fluxes themselves. Now, these fluxes, they melt and they cover the weld. So in some types of welds, the protection of the molten metal from the air is by this flux that melts and becomes a slag. A flux and a slag are more or less the same. The difference is the flux is what is before you weld, and the slag is what it is during welding when it's molten and after welding. Have you seen welders chipping things off after welding? Right? Have you seen that? People weld and go, puck, puck, puck. Okay. What they are doing is chipping off this slag that was left over the weld. Briefly, why do we need a slag? So if I have molten steel, what do you think is going to happen in a normal atmosphere?
It's going to react with oxygen.
Of course, and nitrogen, everything bad will happen, right? So how do you prevent it? There are two main ways of preventing this in welding. One is with these fluxes and the slags that create a barrier of molten glass on top, right? And this is good because since it stays on top, you can have a huge weld or a very long weld, a very long molten tail, and it's all protected. What is bad is you need to chip it off. The other way about it is to have what is called a shielding gas, and I don't have this listed. in which you blow argon or helium, right? Or whatever thing that is expensive and inert, right? And that would protect your weld. And then you don't need to chip off anything, and it looks very clean and easy. But the gas is expensive, and also you have two other problems. If your weld has a huge molten tail, it's likely you'll not cover it because the gas is concentrated in an area near the weld. The other problem is if you're welding outside. What do you think about using a shielding gas and welding outside? What can happen? It blows away. And then you paid for the argon that went downwind, and you're having all this air, like causing a reaction in your steel. When steel is not shielded, it looks like Swiss cheese. So it is a problem you very quickly notice. More terms you're going to see in our lab. A manipulator. A manipulator is an arm that manipulates your torch, moves left, right, up, and down. Okay, that's a manipulator. You'll see it in action. But then you have something else called a positioner. A very important word for welding is position. What is the position of the weld? Here, welding diverges from machining very much. In machining, you can mill upside up, upside down. You can do everything, and who cares? But in welding, the gravity vector matters because you have molten metal and has a density of about 8 in the case of steel, right? So it's not the same to weld upside up than upside down, right? And I'm going to tell you in a couple slides that they have names for those things. So the positioner, what it does is put the thing in position for you, right? Imagine you have a pipe. Sometimes you have to weld the pipe all around, and here at top is good, and here at the bottom is bad. Or maybe you can roll the pipe. If you can roll the pipe, that's what the positioner does. The positioner keeps your pipe always in the good position as it rolls. Orbital welding is what happens when you have some sort of machine that will weld, but you cannot roll your pipe. So for example, in this case, there's a huge pressure vessel, and this bug is holding the torch, and the torch is moving around the seam, right? And in the case of, this is, how many of you have taken heat transfer? Okay, yeah, some of you with me, right? Like heat exchangers, the shell and tube heat exchangers that have lots and lots of tubes. How do you seal the tube to the bulkhead? Not trivial. If you do it by hand, it's going to take forever, and that's the way it used to be. But now there are machines that do this little orbital welding at the bulkhead. So I visited one of the companies that makes heat exchanger for the nuclear industry in France. And those things have thousands of tubes. They're bigger than this room in cross-section. Many, many tubes. The lead time of those is months. The guys will be welding for months these tubes to the bulkheads, right? Pretty crazy. And they do it with machines. If you had to do it by hand, I don't want to know. Here you have some welding terms. I'm going to dwell on 3 only. Manual welding is when you have this stick, which you will do. You move the stick. There is no moving parts in that. Then you have semi-automatic, that in reality, in my mind, is nothing automatic. But if you have a wire system and it's continuously fed, right, the wire is continuously coming out, they call it semi-automatic because the advance of the wire feeding is done by the machine. That's semi-automatic. And then automatic, or they don't tend to say automatic welding, but they call it mechanized. When you grab your weld, right, for example, this case is a mechanized weld because you put the welding torch on top of something that is moving it, right? And then there are some other subtleties about once you start to automate more and more and more, what you call it. These are the definitions you were talking about. So these are the definitions from the American Welding Society. I forgot to mention in the first slide, these definitions, these words are defined in a standard of welding terms. I very highly recommend you download it, right? We have access in our library. These are very expensive standards. You have the blessing that as students you have access to this. go and download it through Novel, right? So all these things are in those standards. We're going to have a class on codes and standards, but there is something I wanted to bring up. Something called, if you remember the first class, I said in welding, right, you have the welder that is like a musician, but somebody had to write the piece for the musician, right? Somebody had to write the music sheet. So the music sheet is a welding procedure specification that says, what should you do? How many volts? How many amps? What velocity? What electrode? All this, right? This is a welding procedure specification, and it's called WPS, right? And there is something else that comes before. That is the PQR, that is Procedure Qualification Record, that says, if I do this current and this voltage and this electrode and all this, I'm going to get this value of hardness, this value of strength, this corrosion resistant, and this is the document that proves that the music sheet is going to accomplish the intended goal, right? Very, very important. So the welder sees the WPS only, because the welder doesn't need to know what is the final hardness. The welder needs to know, what should I do, right? But the engineer, especially if something goes wrong, needs the PQR to say, okay, this was done right. So among the welding people, and those are the real practitioners, not like me, they think a good joke is to say, oh, they did the PQR after the WPS, haha, right? But it's kind of a somewhat of a sad joke. Very often, you tell the welder what to do, and then you realize, oh, I didn't check if what I told the welder to do is going to be what I needed to accomplish. So they tell the welder what to do. The welder spends days welding, and then somebody says, how do you know you're going to get the hardness or the tensile values that you want? Oh, and then they go and they write the PQR afterwards. That is super bad. That should never happen to you, right? So it's kind of these insider jokes about doing it backwards. Bottom line is the music sheet exists, and it has kind of two components. One is what the musician reads, and one where it's shown that it will give us the intended results. How about this? Look at all these acronyms. I'm not going to read them. Each of these, you see that most of them end up in W. All of them end up in W is because it means welding, something welding, 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 welding. The AW, right, means arc welding, arc welding, arc welding, right? The big spark. And then, for example, the first G means gas. And GTAW means gas tungsten arc welding. And GMAW, gas metal arc welding. This is flux core arc welding. All these things will become second nature to you. Who came up with these acronyms beats me. They are unpronounceable, right? And a funny aspect of welding is that although we have this official name, gas tungsten arc welding, and some people call it GTAW, some people call it GTAW, I don't know what else to call it, right? In the end, what people say is call it TIG. That is the old name, and still used in Europe, that means tungsten inner gas, right? So very often I will say TIG, and I'm going to write GTAW, right? It's kind of funny. Same with GMAW. I might say MIG and write GMAW, right? And there's a difference. MIG and MAG, we're going to discuss those when we get into that unit, right? Other things are like friction stir welding. This is a solid state process. Okay, acronyms, more words. Okay, here things start to get interesting. You must know this, and this will be one of the questions in the exam, right? These are joint configurations, and there are 5 main joint configurations. This is not a mathematical taxonomy, so I don't know if you can prove mathematically that it's 5 and not 6. But this is the way welding goes. And I keep thinking, I would love to do this like from a very fundamental point of view. Another thing is like funny names in welding, the butt joint, right? So, and you have different types of butt joints. You have the square butt. That means you have a plate, you have another plate, you put it together, right? Because it's just cut 90 degree, and the other one is at 90 degree, you put the welding on top, square butt. But it can be open, so you have an open square butt joint. You might cut like a chamfer in one of the plates, right? A bevel, and that's called a single bevel. But you might want to cut a bevel on both sides. Then it's called a single V, right? This is not called a double bevel, okay? This is not a double bevel because this is a double bevel, okay? You must know this, yeah.
So if I were to have two double bevels together, would that be a double V?
Okay, here it doesn't appear, but you mean two V's. Yeah, that would be a double V, right? But the same way you have like a double U here, right? Or a single U, right? Or here you have a J. That's about butt joints, right? And here you have some with a backing plate, some without a backing plate, just for show. Let's go to here, corner joints. Corner joints, you typically have fillet welds here, right? This is a V joint, a V groove, right? A single V here. But this, when you weld from inside, right, and the corner is what makes your groove, that is called a fillet weld. We're going to have a whole unit on how to size a fillet weld. Here you have what is called a lap joint. You see the plate is coming one way and the other is that way. It's like this. This is very used in the auto industry. And it's all, but they use it with thin sheet and they would use spot welding. In the civil constructions, they also use a lot of these lap joints too, but with thick plates. Then you can have a T-joint, right? And in here you would have a fillet weld, right, on one side, or here you would have two fillet welds, right, a double fillet. This one I left for last. It's not a very common type of joint, but it's when you weld, it's an edge joint. Of course, you weld at the edge. You're going to see lots of this in the practice, the old exams for practice. And you see here, this is the symbol for all these things. So I'm going to, relatively soon, show you those symbols. About joint preparation, I wanted to discuss why would you do a single bevel, a double bevel, or a J groove, right? So this is awesome. This is cheap. You didn't need to do any preparation for one of the sides, and you just could cut the other one in many easy ways, for example, with flame cutting, right? This is very cheap. What is bad about it? Well, you need to fill all the area of this triangle with metal, which is expensive in metal and time consuming. This is also good because I have access, I need access only from one side. This other one, right, is also relatively easy to do, right? And if you do the mathematics, you're going to come to the conclusion that this one requires about half as many passes, half as much metal, which is kind of convenient, right? So you would do this weld twice as fast as this. Also has smaller distortion because now the distortion forces are evened out, right? Or more or less evened out. Why wouldn't I always do this instead of this? Say? No, actually, if you have half the number of passes, the amount of heat you put in is about half. You need access on both sides. So if you're doing a pipeline, you better have a rather small welder to curl in, right? So typically, you don't do this in pipelines. You would do this in for example, mechanical construction, right? And finally, you have the J. The J, you can have access from only one side. That's convenient. And because why do you have to cut this opening? Have you thought, why do you need to cut an opening and not just have something narrow? Why? Why do I need to open up my weld?
It's easier for the metal to go.
Right, well, it's easier for the welder to get the torch in, right? If you do something too narrow, you cannot go in. So the catch is that when you're committed to this, the space here might be okay, but here the space is too much, you're wasting it. So you can do this J type of bevel. In the J bevel, right, you have good enough room at the root, at the bottom, but then when it comes up, it doesn't come up opening all the way. It starts to turn, and it's not so big. So it has many advantages. What is the disadvantage? This you need to machine this joint. You cannot just flame cut it and go with a grinder, right? So do you have this thing for machining the joints? If you have it, this is awesome. If you don't have the machine, you have to think, do I want to do this capital investment? In welding, everything you can do, you want to do, you can do it. If you want to do it, you can do it. You might not want to pay for it. That's a catch. So as we talk about welding, and we're going to have formulas and science and lots of amazing things, you're going to see that the real deal is not whether you can do it or not, but is, can I do it in an economic way? Do I want preheat, or do I want post-weld heat treatment? Do I want a bevel joint, or do I want a J joint? There's always a trade-off, and this trade-off is different for every shop. Narrow gap welding, if you need to weld something that is really thick, like in the nuclear power industry, like 1 meter thick, okay, for sure you're not going to be doing a bevel. For sure. If you do the numbers, it will tell you that in 100 years you don't finish filling, right? So you might do a J groove, and it's still not good. You do J's in pipelines, but not good for nuclear. So you do a narrow groove that is essentially something so narrow, torch looks like a knife. So I have a couple of videos here which I'll play for you quickly. I don't know who was the graphic artist that thought that making a shaking electrode was a good idea. The electrode does not shake, right? This is the groove, for example, right? And here they are comparing the different levels. And here you have the video in action as it is on spooling. So the productivity here is a lot bigger. I hate this shaking. Now these welding torches look like knives. Go in. Very difficult to do. Very difficult to do. More things that will be in the exam. Parts of a groove weld bead. So each of these, you have this part here is called the root. At the bottom of the weld is called the root. And the root can be touching or cannot be touching. If it's not touching, you have what is called the root opening, right? And it's not sharp as a knife, because it makes no sense making it sharp as a knife, because you're going to melt that part all too quickly. So you square it off, and this is called the land, or the root face. Here you see that it's a little bit square here. And then you have your bevel, and you have the bevel angle, and then you have the groove angle. Now, more funny terms in welding. The welding has a face. And the face is what you see. It's the top of the weld. That's the face of the weld. And the weld, funny enough, has a toe, right? Now, it's really funny when your toe is right next to your face, right? But that's the case of welds. The toe is right here at the edge where the face of the weld meets the plate. Then you have something called a throat. It's very anthropomorphic. Huh? The throat is the area through which the weld would have resist the strength, right? And in this case, the throat could be from here to here. This would be the actual throat, which I haven't marked. And this other part, from the top of the plate to the bottom of the plate, would be the theoretical throat, right? Because very often you say, I don't know how big my reinforcement is going to be. I don't know how big my melt through is going to be. So I'm going to assume they are not there, not take credit for that, and just assume this is my throat. This part that sticks out, this is called the reinforcement, right? And then something in which we are also going to discuss quite a bit in this class. You see this part that surrounds the weld? If you do the metallography, you're going to see that the metal there is all funny. That's called the heat-affected zone, right? A heat-affected zone means the heat somehow affected it. And we can do lots of calculations about that. Extremely important. Most welding problems are in the heat-affected zone. I'll tell you why. If I have a problem with my welded metal, I can choose another weld metal. And better and better and better weld metals, even if they're expensive, I can choose. The heat-affected zone is on the plate. So I will never fix a heat-affected zone problem with filler metal. And very often, the welder or the welding engineer has no say on what the plate would be. So the US Navy was involved in the design of making super high blast resistant steels, right, in the 80s. Right? These steels were awesome, but then you need to weld them. And when you weld them, you ruin the properties right around the weld, and they were not good. Conclusion, they have the awesome steels, they don't use the awesome steels because of welding, right? These problems in which the heat-affected zone will not be kind to you. Remember fillet welds I mentioned, right? And in fillet welds, you also have a face, you have the toes, have the root, and now you have the leg, right? Here's the leg, here's the toe, here's the face. The leg is how far you have to go with the weld over the metal. So they would have gauges that go from this wall here and measure up to here, and you would see what your leg is. So the legs have toes, faces, legs, throats, right? This is the actual throat, and the theoretical throat would be if I were to make a triangle here, right? That would be the nominal throat. Lots of words. We're going to be using it now. Okay, let's see if we're on top. Which is a toe? F. F is the toe, right? You're right. F is the toe, right? What is the face? E, right? Or N, right? I don't remember what the difference between E and N in this case is, right? Because I was asking people to, but this is the face here, right? Okay, so we're doing super well. What type of joint is that? What type of bevel joint preparation do we have here? A J, right? A single J, right? So this is likely to be something like a pipeline, for example. In carbon steel, the passes have names. First pass is a root pass, right? Because it's on the root. Super important, because if you're welding a pipeline, this is the pass that is going to be in contact with the fluid. So if you do it wrong, this is the one that is going to corrode or where cracks can initiate, and is the most difficult to inspect. So this is crucial. The most important part, if somebody ever gives you a pipe to inspect, you don't look at the surface. That is what I used to do. Right? And you say, oh, good weld. No, that means you know nothing. People who know welding for real, you give them a pipe, and they look inside to see the root. Then you know. Well, at least you don't show yourself you don't know outright, right? So this is very important pass. Right after that is something called the hot pass. We're going to see lots of things, but it typically uses different electrodes for the root and the hot pass. The root pass often has hydrogen. We're going to see why, and we're going to see it's a problem. So when you do the hot pass, that means it's a pass in which you go slower and everything gets very hot, so the hydrogen can go away, right? And then after you did your root pass that has lots of hydrogen and the hot pass that drives the hydrogen away, you do what is called filler passes. Can be few or can be many. And when you finish a weld, you have the cap passes. For a welder, cap passes are everything, because that's what you see in visual inspection. So doesn't matter what you do, the cap pass is going to look good, right? Because that's what everybody sees. More things to learn, and I'm sorry for that, but this is the language. And if you look at all the exams, you're going to see how we asked about this. Remember when I say gravity matters? So there is a name for the positions. I'm going to teach you the North American way, and I'm going to teach you the European way. The North American way is the easy one. It's called flat. It's not called horizontal. It's called flat, right? So I tilted 90 degrees, right? Like here. And this is position 2. So position 1, position 2. The F is for fillet. The G is for groove weld. Okay? 1 F, 1 G. 2, right? So if I now go vertical, whether it's up or down, in North America we call it position 3. F or G depends on groove or fillet. And if we go overhead, we call it 4, right? And now is exactly the opposite of position 1, 4F or 4G, right? This is just naming. For pipes, if I'm rolling the pipe, easy, that's position 1. What is holding the pipe if I'm rolling the pipe? Do you remember what it's called? The positioner, right? Because it keeps it in position. And now, if it's a pipeline in which is kind of rather difficult to rotate the planet, right? Like you go around, right? And this is they call it position 5. Position 5 in reality is a combination of position 1 on the top, position 3 on the sides, and position 4 below, right? And then when you qualify welders, right? You seldom do this in practice, but when you qualify welders, you give them this position 6G, in which they have to go through everything in an inclined situation, right? This is difficult. This is typically used to qualify welders. All right. Which is a welding position here? 6G, right? It's not a fillet, so we know nothing with F is going to go. And it's at 45 degree, right? And it's welding around the pipe, 6G, right? And if you look at all the exams, you're going to see we ask things like those. The European system is a lot more rational, right? We don't use it, but it's so easy to remember. Is what we call position 1 here is called PA. Now what we call position 2, right? They have something intermediate. They have position B at 45 degrees, position C, PC at 90 degrees, right? And you go like this. And also, they discriminate between what is called vertical up and vertical down welding. Very different, because the weight of the molten metal is going to push either towards the front of the weld or to the back of the weld. Sometimes you want one, sometimes you want the other one. Right? And they discriminate. Well, in North American notation, naming, position 3 is 3, right? And you have to clarify somewhere else if it is up or down. 2 things. Important quantities in welding. These are the few slides here, and then I want to go into symbols. There are 2 concepts that matter a lot. T85 is one, that is time to cool from 800 to 500 degrees C. Now, this matters a lot for steels, right? And it's only for steels. Do you think T85 matters for aluminum? Aluminum melts at 660, right? So this is a concept for steel. Now, what happens is we use steel so much that this became a very common way of checking how fast you're cooling, right? Now, T85, why do you think they picked 800 to 500? Anybody has a thought?
Sensitization.
Say?
Sensitization.
Okay, sensitization, but that would be for stainless steels, right? But in carbon steels, you don't have that problem, and you still use T85. Transition, right? Like you take the austenite decomposition happens around 727, right? Right in between there. So by looking at how far you go from 800 to 500, essentially you have a sense of how fast you're going through the austenite decomposition. And that would tell you are you likely to have perlite or bainite or martensite or whatnot, right? This is typical for carbon steels. The other thing is heat input. And by heat input, we talk about kilojoules per centimeter, not watts. That means how much energy I put in each length, right? For example, if I'm welding one stringer bead and another weld in similar parameters, but it's a weave bead, which is going to have higher heat input? Say? Stringer higher heat input? I think the weaving, because I'm putting lots of heat and advancing little, right? So heat input matters. And if you remember, we said that as we weaved, we were going to have a slower cooling, right? So we get to see again, like these issues of heat input, in which putting a lot of heat in a short distance means a lot of time to cool down, right? And putting little heat, like in a stringer bead, means little time to cool down, right? Which is going to have a larger T85, something with low heat input or something with high heat input? High heat input is going to give us a long T85, right? So you start to see how all these things connect, and these things go together with the math. So heat input, this is very important. People seldom speak clearly, but there are two heat inputs. One is the nominal heat input, is how much do you think you're putting into your material? That's the nominal. And then they say actual heat input is how much actually went into the material. Of course, they are related by an efficiency, and the efficiency is never 100%. If you're near a weld and you feel the heat, that heat you felt is a heat that this plate didn't feel, right? And actually, that's quite a bit. And we're going to have a unit just on these efficiencies. So nominal heat input. The notation, when you see formulas, you're going to see that sometimes we contradict ourselves on what symbols we use. I'm trying to have a universal notation. Has been very difficult. We will prevail, but every year we find new things. So this is the power. This is the power, for example, of a laser beam, or the power of your torch divided the travel velocity. That's the nominal heat input. In the case of arc welding or electron beam welding, that both are processes based on electricity, the power, and I understand you had a precious little background on electricity, but some of these things you'll have to learn. And probably you already knew that power is voltage times current, right? So in a laser, power is power. But in electrical processes like arc welding or electron beam, voltage times current. This is a very common formula. So I'd like to give you 3 minutes. Oh, OK, so typically it's like about 10 kilojoules per centimeter in our province. If you do automotive, it's about 3 or so. And we already discussed what low heat input and high heat input means. I like to take 3 minutes and have you guys go over this problem, right? What is the nominal heat input in this butt weld? If anybody takes that. So we said voltage times current divided velocity. So maybe this helps there. We're talking about this one. Anybody gives me a value? I see many of you not calculating, but if I get 1, I'm going to be super happy, especially if it is right. But let me give you a heads up. The reason I'm asking you to do this is because typically more than half of the class gets it wrong. And it's not because it's difficult, it's because we're seldom used to try to put numbers together that have physical meaning and we seldom take them seriously. Right? Probably many classes you were doing Mickey Mouse problems that were not with real values. 4,600 what?
Joules.
Ah, but what did I ask there?
Okay. Then it's for 46
Joules per what? Centimeter. So you say.
Oh, no.
You see?
That's meters? Yeah, right? The travel speed?
4.4 meters per minute. Yeah.
Oh, what's the difference between the one that says WFS and the one?
Oh, sorry. This is wire feet speed. Wire feet speed. So you want the travel speed,
Yeah,
right?
right?
Okay. Yep.
Okay. Yeah.
What have you gotten? People live and die by this number. So you're going to hear all the time about the heat input in practice. Doesn't this look like a trivial calculation? Actually, it is, huh? Anybody got a number?
Uh, 46.06 kilojoule per centimeter.
For 46 kilojoules per centimeter. Okay, so I mentioned that here in Alberta we weld thick things and it's 10 kilojoules per centimeter. And this is a thickness of 1.5 millimeters, and you say 46. So I tell you right now, that sounds like high to me. Okay, I'm gonna put you guys out of your pain. See here. You do this number. The catch is they give it in meters per minute, and you have to divide by the 60 seconds, right? You guys will be doing this in the exam, and you're going to be doing it right. But this is the type of thing we should be able to do like this, and of course we don't, and neither do I, right? Here's a calculation, 2.76. I told you in Alberta about 10, but here, in this problem in concrete, this is kind of automotive sheet. 2.76 is about 3, yeah, small weld, right? Cool. So I have 15 minutes now. Do you guys, for going quickly over welding symbols, do you have any questions about naming, other than, do we really need to learn all this? And the answer is yes. Okay. This heat input matters so much, and it goes into formulas, and the T85, the time to cool from 800 to 500, also goes in formulas. All right.
It doesn't matter if we have DC or AC.
This is just a heat transfer thing, regardless what the source of energy is. Can be AC, can be DC, can be a laser. Now, what you're going to see, and sorry, somewhere it matters. When I said voltage times current, I was assuming voltage and current were constant, like CC or CV. So I wasn't clear on that. Now, if you were to have waveforms that are very complicated, in reality, this would turn into an integral. But you don't need to do the integral. The welding machines, as they weld, they measure things and they do the integral themselves, and they will tell you, this is my nominal heat input, or this is the nominal energy I put out, right? Yeah. So.
I was going to ask you just that, like, the power source itself is going to be one, but the actual
Plate sees something else.
Yeah, it's going to be.
Yes, there is a factor that relates what the power source believes it did to what the plate saw, really. And that's really an efficiency, right? And depends on quite a few things. Okay, so let me get into welding symbols. Okay, I'll go quick, but again, this type of thing, welding symbols. Please download this. This is super clear, the standard. And the figures I use here in class are the figures from the standard. And those are expensive, and you're students, and you have access to them, and you can learn, and you can be awesome. Look at this. This is actually an actual blueprint sent to the shop for fabrication. You see things like this? Those are welding symbols, right? Doesn't it look like you'll never make sense out of this? I mean, that looks pretty intimidating to me. But the person who must read this and act upon it have far less studies than you have. Isn't that incredible, right? So we should at the very least be conversant and not be intimidated, but be able to go and divide and conquer and say, okay, let's see what this is, right? Let's see what other symbols are that are all around, right? Okay, so this is kind of a summary, but the welding symbols all involve this arrow here. You have an arrow and a baseline, what they call the baseline and the arrow. And this is called the tail. And then you write things around them. This is for your summary, but I'm going to show you what you do, because actually this looks more complicated than it is in reality. So remember the type of joints we discussed? Butt joint, corner joint, the 5 types of joint. When you put the arrow, and for something that I cannot understand why it happened, I don't know, but we have to accept as it is. If you put this arrow here pointing, what you write on top of the arrow is what goes on the other side. And what is in the bottom of the arrow is what goes on this side. Why? Why? I don't know. I wish I can have power for a day. And this is one of the first things I would change right after peace in the world and stop hunger. Why? Look, here I put the arrow. This arrow here means this. Oh, but I have this arrow here. Okay, this means that. Why? Right? But it's the way it is. You just take it and move on. Acceptance. Acceptance is the key here. Here, I put this arrow here. What I wrote on top of the arrow means the other side. The way it is, every year in the exam somebody will do it backwards. Number one thing, you have to do it right? Here's a lap joint. And I didn't put here, I think, the edge joint, but there is same story. Symbols. Remember when we talked about joint preparation, the square butt, the bevel, the single V, the double J, or those things? They have a symbol, and the symbol is quite self-explanatory, right? Look, it's not difficult to remember this is a square butt. It's not difficult to remember this is a single V. Not difficult to remember that this is a single bevel, right? These are all tabulated. You have it in your notes, and the standard says everything cleared, right? You can have a J. We didn't talk much about this flare bevel, but when you are welding rods or things like rebar, sometimes you weld it there, and it even has a symbol for that. Here you have the square, V, bevel, UJ, all those things. This triangle, that's a fillet. We're going to be using this a lot, the fillet. Plug welds or slot welds, we're not going to be using very much. So much to say about them, right? This is a backing weld, right? That is, you're going to see an example, right? More symbols. Remember the first thing I showed you had this symbol of a welder all around. It's fairly easy to remember, other than you just have to always do the mind twister that what is this side in reality is the other side. But the flag means field weld. This black dome here means melt through, right? So don't just stop at the root, go a little bit farther. And these are symbols for finishing. Are you supposed to have a flat weld, or a little bit concave, or a convex, or a little bit concave? You can make them speak. These things speak, right? This is the language with which you communicate with the welders. Some symbols have no side significance. top and bottom, right, are the same. So in this case, you can get as confused as you want because it doesn't matter. In this case, you cannot. Look, I introduce you to your first real welding symbol. Here, I want to make this weld here, right? This is single V, right? And it has some amount of melt through that they didn't put. But what matters, here you have the V. You put the arrow here, but you have to draw the weld on the bottom, right? And you weld it upside down, right? The root always goes against the baseline. Oh, you draw it with the V up. That means you have to weld from the other side. You follow this? This mechanics is kind of backwards, but once you think about it, you can get used to it. No side significance. This is not a big X. This is a double V, right? One V one side and the other V the other side, right? Lower distortions, right? But you need access on both sides. You start to see how things come together. Practical aspects, distortion aspects, economics, symbols. Welding is awesome. Welding is a single thing, and it's everything. It's kind of some sort of Buddhist concept. Okay, so symbols with side significance. You see the melt through here? Here they put. This is this little black dome there. And again, funny, why? If the melt through is here and you put the arrow, right? This means the other side. This means this side. A single V groove weld. Here you have the melt through too. What does this 1/8 mean? Right? This 1/8 right next to this melt through means the depth, how much you want the melt through to stick out. Right? Sometimes you say nothing. Sometimes you want to say it. You can say so much with these symbols. Here you have an edge weld, right? This is an edge weld that would come here, but you melt all this edge and becomes something that actually more resembles a butt joint. But this is an edge weld. So you have the edge weld here and the melt through. That means you go all the way to the other side. And they didn't put any number here, but you could have put a number. How deep you want to go there. Fillet and plug welds. Let's focus on the fillets. Here you have the symbol for fillet. And something interesting, you always draw the fillet like this. And so if the weld would look the other way around, doesn't matter. You always draw the fillet like this, with the tall side to the left. All right? Not the other way around. That's a standard. Look, if you want to make this weld here, let's look at one of the possibilities. You have your arrow, you have your baseline. Here it says you have a fillet. What fillet is this one? Let's say 1, 2, 3, 4. What fillet is this one? This is fillet 1, right? It's the other side. The other side here, not the other side here. Okay? So the other side. And this is fillet 2, right? And it says 3/8. That's the leg. When in a fillet they give you a 3 millimeter fillet or a 5/16 fillet, that means what the leg is, right? That's the unit of measurement of the metric of the fillet. Yeah.
Do the legs have to be the same length, or?
No. If you want it, the standard tells you how you specify it. Fillets do not need to be what do you call it, isosceles triangle. They can be anything. Now, that said, almost always they are like 90 degrees and 45, almost always. But they don't have to be. And actually, fillet doesn't need to be a single pass. A fillet can be an enormous bunch of weld, right? And then you can play any games you want. So you know how to read this, weld all around. This S here, what type of weld is this? What type of joint preparation, what type of weld would I be doing here with this symbol? Fillet, right? That's a fillet. And this S means the size, and would be the leg of the fillet, and goes all around. You see, it starts to speak, right? remember when we talked about stitch? So if you're going to stitch your weld, you can say how long the stitches are going to be and how separate they are going to be, right? And it's length of the stitch and pitch. So you specify how long the stitch is and how separate the stitches are. No, you don't specify this gap in between. So in this case, right, what you're saying is on both sides, you're having a stitch, a fillet, that has this length and this separation. For example, here. In this side of the weld, you have this 812, means 8 millimeters long, 12 millimeter pitch. It's interesting. How about this? You wanted to stitch them and stagger them? You can specify that, and you specify it by staggering the fillet symbols, right? That means this. And here we have the 4-inch, this is clearly in inches, like a 4-inch length of the stitch and 14-inch of pitch. And the 1/4, right, would be the 1/4 leg. And no, you cannot ask, is this a throat or the leg? No, that's the leg, because that's the way it is. It's debatable if that's the best way of doing it. The Welding Journal has an article this month saying, we should specify the throat. Everybody specifies the leg, and you cannot change it now. Groove welds. Here we have one way of specifying, right? You could specify this other way too. From the bottom, the same weld. Look at this one. In this one, this block means the steel backing, and they put an S. That means steel. There are other symbols too for what would it be, the backing, and they are not as standardized as we would like. 1/4. This 1/4 here is the root gap. This is the root gap here, and this 45-degree is the groove angle. So now we're saying a whole lot of things, right? And what we're saying here, 3/4 and parentheses 3/4 in this case wasn't necessary. But sometimes you might have a partial penetration weld, right? You say what groove you want to have, and you want to melt more than that groove, right? So you have to specify what groove preparation you're going to have. This is the groove preparation, and this is how much penetration you actually want, right? Those are more sophisticated things. They are all explained very clearly in the standard that you have direct access. Right? Okay. So here they're saying in the backing plate what size of backing plate you should have, right? 1-inch width, which they didn't put, but 3/8 in thickness. One more thing, because I think we'll need to stop soon. 2 more things. One is this has a double bevel, right? It's not a V, it's a double bevel. This is your drawing. How do you know in the drawing what side to make the bevel? Right? You need to specify it, otherwise the welder is going to do whatever they want, and maybe it's not what you wanted. So if you want to say this side on the right, this side is where the bevel goes, you make a break line. Right? And the broken line where it points is it points to the side that needs to be beveled. In this case, you would have put the arrow straight, right? But no, you have to break it, and then now it's clear. If you break the line, it's clear. If you don't break the line, you do whatever you want. The other is sequence and combinations. For example, here it says you have a bevel weld and a fillet weld, right? And here you see on this side, right? On this side you have a bevel, a single bevel, and on the other side you have the fillet. He's speaking. I don't know why they want to do it like that, but they are telling it very clearly, right? And here too, you can say it that way. And the break says in which way you should do the bevel too, right? I think it's pretty cool. this is sequence. When you have combinations with a sequence, these sequences are interesting. Here it says, your weld should have on this side a bevel and a fillet, and on the other side a bevel and a fillet. You see here you have the bevel and a fillet. They didn't make the separation there, but these are 2 welds. In total you have 4 welds. But you could have specified like this, saying, first, you read it from the arrow head out. So first, you do on this side a bevel and then a fillet. And then on the other side, you do the bevel and the fillet. This other symbol says something different, says something that would likely give you less distortion. It says, first do both grooves, and then do both fillets. The thing is speaking, right? You're telling the welder what to do, how to do it, when to do it, and if you start putting numbers here, you're saying you're saying everything. It's a book, right? So about weld order, this is all I wanted to show you, and I think we're just a couple minutes past. I'll see you next Thursday, and we're going to go on Thursday from here to our lab to do the safety, the lab tour and a safety introduction. Let's stop here. Thank you.